So these are some problems dealing with estimating the area under the curve, possibly in a Calculus 1 or a Calculus 2 class. Here, maybe end of Calculus 1, start of Calculus 2, perhaps. First problem here, we're going to estimate the area under the curve y equals x cubed minus x from x equals 1 to x equals 4. And number one, we're just going to it's actually the only problem we're going to do. We're going to do this in, I think, a whole bunch of different ways, different numbers of rectangles. We're going to do upper sums, lower sums, midpoint rule here. So first one, we want to use 3 rectangles and a lower sum. So picture of what's going on here. We've got y equals x cubed minus x. That's this function here graphed. So we have our origin down here. Might be not quite there. Actually, this is x equals 1 here, so not quite the origin. But you have some graph here. And what we're going to get is we're going to take a rectangle from 1 to 2, from x 1 to 2. The height is going to be sort of the lowest value of the function on that interval. Note our function, if we go back to our function, it's x cubed minus x. So if you did 1 cubed minus 1, gives you 1 minus 1, that gives you 0. So our initial height is 0 here. So this first rectangle doesn't really show up because it has height 0. Next one is height 2. Let's see, 2 cubed is 8 minus 2. That should be height 6. Looks plausible there. So then I get a rectangle height 6 with 1. Note our scales are different horizontally and vertically. Next one, we're going to plug in 3 is going to sort of be the minimum when we go from 3 to 4. So we have a rectangle of width 1, height is 3. So when we want to estimate this area, all we're going to do is add up these 3 rectangles. Note again, the first rectangle is sort of height 0 there, so it kind of looks like 2 rectangles. And so when we do that, what our area is going to be really, it's sort of our, well, y when we plug in, say, the left endpoint. Let's call that 1. How about we call this function f of x is x cubed minus x. So I'm going to take f of 1, that's the left endpoint, times the width. Well, each rectangle, there's a width. 4 minus 1 is 3. Divided by 3, each rectangle should have width 1. And the next rectangle has height f of 2, still width 1. Next rectangle has height f of 3, width 1. So again, what that is f of 1, we did that up here, that's 0 times 1. F of 2 is 2 cubed minus 2. 8 minus 2, that's 6. So I'm going to add 6 times 1, or 6. F of 3 is 3 cubed minus 3, which is 27 minus 3, that's 24. So I get plus 24 times 1, that's really 6 plus 24. And our answer for our first estimate is 30. Okay, so we're sort of done here. Let's just look at sort of what's going on in our picture here, though. Note, the actual area under the curve is going to be much bigger than 30 here, or somewhat bigger than 30. Now, we're missing all of this area here, all this area here, all this area there. All of our rectangles are actually underneath the curve, and that's what happens when we do a lower sum. In this case, we're also taking left endpoints. Turns out they're the lower endpoints in all instances here. Sometimes you do left endpoints or right endpoints. Next question. We're going to use 3 rectangles and an upper sum. So very similar picture here. What we're going to get, instead of a lower sum, we're going to get an upper sum. Here's 3 rectangles. And so when we go from 1 to 2, our height, instead of being at the sort of lowest value of the function on that interval, it's at the highest value of the function here. So what we're going to get, same thing from 2 to 3, 3 to 4. So what we're going to get here is this area is going to be, well, its highest value on from 1 to 2 is actually at the right endpoint, f of 2. Width of the rectangle is still 1. The next rectangle, that is from here to here, the highest value is at 3, so that's f of 3 times 1. And the third rectangle, this height is at f of 4, or the height is at 4 that we're going to use. So we're going to get f of 4 times 1. We've already evaluated these. This was 6 times 1. F of 3 was 24 times 1. F of 4 is 4 cubed minus 4. That's 64 minus 4. That is 60. So plus 60 times 1. So we get 6 plus 24 is 30 plus 60. Here we're estimating our sum to be 90. Here. And in this case, that's actually going to be too big. So we had 30 is too low, 90 is too big. This is too big because we get all of the area under the curve, but then we get this extra stuff up above as well. Okay, so our goal here is really to get a better estimate. We had one that looks way too small, one that looks way too big. How do we sort of average these? Well, there's a couple things you can do. One of them is, in general, I'm going to use what I'm going to call the midpoint rule here. So I'm going to do 3 rectangles, and instead of picking sort of the highest function value from, say, 1 to 2, when we do this, so this was the largest function value, or we picked the lowest function value before, we're going to go really to 1.5 and sort of think that should be about in the middle. So that's our goal. That's not always going to work out sort of exactly, but that's really what we're going to try and do. The picture of that looks like this. So here's our height at 1.5. We get this rectangle. 2.5, we get a height there. 3.5, we get a height there. So it's really, we're taking the midpoint of 3 and 4. That's 3.5. And now the idea is this shaded region should estimate the area under the curve. Now, it's not going to be exact, but this area here, this is sort of, we're counting this as an overcount, but we're missing this here. So the idea here is this part here should be about the same size as this area here. So we get sort of the shaded part above, and the unshaded part below should kind of cancel out here. Note, they're not going to exactly match. It may look like perhaps they do, but they're not going to be exactly the same here. But it should be a better estimate than what we've been doing, still using 3 rectangles. So what we're going to get here is our area was going to be f of, well, how about, we'll do 1.5, which is really 3 halves. Let's just do it that way. Let's do 1.5 times the width, 0.5 times the width is 1, plus the next rectangle. We're going to go between 2 and 3. That's at 2.5. Width of that rectangle is 1. So here's 1.5 with 1, 2.5 with 1, 3.5 with 1. So we're going to add to this f of 3.5, multiply by 1. And then we need to get some of these function values. So this is, let's say it's 1.5 cubed minus 1.5 plus 2.5 cubed minus 2.5 times 1 doesn't really matter here, plus 3.5 cubed minus 3.5. So you add all that up. What do we get? Oops, let's clear our calculator out. Let's smooth this out here. Clean. I get 1.5 to the third minus 1.5 plus 2.5 to the third minus 2.5 plus 3.5 to the third minus 3.5. And that gives me 54.875. So you work that all out, you get something like 54.875. Note our sort of lower estimate from the lower sums was 30, upper estimate from the upper sums was 90. That would average to 60. We're getting something kind of like that here. Still, we're not sure how good of an estimate is this. I mean, again, we're saying sort of this part above the curve shaded should be about the same as the unshaded part below the curve. But there's a detail there when we say about the same. Well, how close are they? Here. So there's another way to get better results here, and that is instead of sort of using a better height, we can go and use more rectangles. So let's just do the lower sum, the upper sum, and the midpoint using 6 rectangles. So what that's going to look like here, let's go back to our upper sum graphic. So we're going to go to 6 rectangles. And I've got a little slider here, 4, 5, 6. So there's 6 rectangles. And now each of these is going to have height, or sorry, width 1/2 here. So we're going to have width 1/2. Again, that's height 0. Width 1/2. And we're doing the lower sums. That's effectively the left endpoint. Here's another width 1/2. So what we're going to do is add up the 1, 2, 3, 4, 5, 6 rectangles here. And so what we're going to get is our area under the curve. Now again, this should be a lower bound. Now it's going to be a better lower bound than we had before. Because before what we did is we took this point and went just all the way over. So we're adding in this sort of part sticking up here in the 6th rectangle. We're also adding in this part here because this rectangle would have went through with 3 rectangles. Same thing this part here. So we're sort of adding in some things that we didn't count before. Still going to be a lower bound, though. So let's write this up. What we're going to use, that first rectangle is going to have height f of 1, but the width is going to be a half. Second one is going to be height f of 1.5. So we have 1.5 as our height. Still going to have width of a half. Next one would be f of 2 times width of a half. And then we get f of 2.5 times width of a half. We get an f of 3 times width of a half. And finally, the last rectangle is f of 3.5 times width of a half. Now, I like to factor out that 1/2. Write this as f of 1 plus f of 1.5, f of 2 plus f of 2.5, plus f of 3 plus f of 3.5. And so what we get is 1/2 times, let's see, f of 1 was 0. F of 1.5 is 1.5 cubed minus 1.5. F of 2 we got before was 6, 8 cubed minus 2. Plus 2.5 cubed minus 2.5 is f of 2.5. F of 3 was 27 minus 3, that's 24. And then we get 3.5 cubed minus 3.5. So this is what we get. Let's see, so we've got the 1.5 cubed, the 2.5 cubed plus, oh, we made a mistake on the previous one here. I didn't get my 2.5, so let's go back up. Correct that first. Whoops, second over. Down, insert, I didn't have a 2.5 there. So it should be 54.375. So let's go edit the answer above here. So this should be 54.375. Just a little typo there. And then, so what we're going to get here is we've got all of these pieces. So I'm going to take that and put this in parentheses. Whoops. Let's do second answer. Plus, we have the 0 plus the 6 plus the 24. But then we have to divide by 2. Multiply by 1/2. And that gives us 42.1875. Again, that's a lower estimate. So we know the actual area under the curve is at least 48.1875, actually bigger than that. We know sort of an upper bound right now is 90. And again, what we did essentially just add up the area of these 6 rectangles. So very sort of straightforward, intuitive idea, a little bit tedious calculationally. It'll get worse, though. Okay. Next one, we want to use 6 rectangles and an upper sum. So same idea here, but we're going to go down to our upper sum. So instead of 3 rectangles, we're going to go shift over to our, whoops, there's 5, 7, 6. There we go. 6 rectangles, upper sum here. So very similar calculation to before. We're just going to sort of do each of these. Now, note, here my area, I can factor out that width of 1/2. I'm going to get the first rectangle is going to have height f of 1.5, f of 2, f of 2.5, and so on. So we're going to get f of 1.5 plus f of 2 plus f of 2.5 plus f of 3 plus f of 3.5 plus f of 4. 1, 2, 3, 4, 5, 6. Note, that's very similar to the last one we did. So when we went up here, we did 1, 1.5, 2, 2.5, 3, 3.5. We get all of this. Again, note f of 1 was actually 0. And so all we're really doing is adding f of 4. So we're going to add down here previous f of 4, which means we should get whatever we had here plus f of 4. And again, f of 4 is 4 cubed minus 4. That's 64 minus 4. That's just 60 here. So essentially, we're going to get this. Instead of typing this all in again, what I'm going to do is I'm just going to use my calculator. Oh, and now I used answers, so it's a little bit problematic here. Well, when I add in, let's just look at what happens here. When I add in that 60, that's going to be 60 over 2. I really should subtract an f of 1 over 2, but that's 0, so I don't need to do that. So what I'm going to do is I'm just going to add 30. So I should get plus 30. If you added that all up, claim is you should get 72.1875. 1875. We could do this. Now, I'm going to streamline this. Let's just go y equals. Get some stuff here from some other things. Let's just do x to the third minus x. Here, I'll put that there. And then what I'm going to do is I'm going to do 1/2 times, and then I can do variables, y variables function y1 of 1.5 plus variables, y variables function y1 of 2 plus variables, y variables function y1 of 2.5 plus variables, y variables function y1 of 3 plus variables, y variables function y1 of 3.5. 1, 2, 3, 4, 5. One more. Variables, y variables function y1 of 4. Close the multiply by 1/2. And if all went well, I should get this 72.1875. There we go. So you could have done this directly. It's just a bit more tedious. You can use the previous calculation and streamline this. You still have to do the previous one to make that work. So there we go. Okay, next one we're going to use the midpoint rule. Now this should be getting better yet here, because our midpoint rule, I guess maybe we should talk about where we are first, is we know our actual area should be somewhere between 72.1875. That's big. It's an upper estimate. Lower estimate's 42.1875. Still a pretty big range, 42 to 72, a range of like 30 here. So midpoint rule, we're going to expect that to be about halfway in between, be like 57 or so, somewhere in there. It's not going to be probably exactly that. Picture. Here, we've got 3 rectangles, 4, 5, there's, whoops, was 6, now it's 7. There's 6. And so we get these midpoints, and again, we're hoping that sort of this part shaded above the curve should more or less cancel with the unshaded below the curve. So we're going to try those. What we'll get here is this area here to estimate. It's again, each rectangle has width 1/2. So you're like from 1 to 1.5, or 1.5 to 2, and so on. And we're going to multiply this by f of the first height will be 1.5. No, not 1.5. Let's look at this. So the first first rectangle goes from 1 to 1.5 in the x. That middle is 1.25. So f of 1.25. Next one, I'm going to increase by 0.5. So f of 1.75. F of 2.25. F of 2.75. F of 3.25. F of 3.75. And let's see, that's it. 1, 2, 3, 4, 5, 6. That works out, and it should be just below 4. So essentially, that's my formula. I'm not going to bother calculating each of those individually. I'm just going to go use the same thing I did before. I'm actually going to go through here and edit this. So instead of 1.5, I'm going to insert a 2. And then we get a 1, insert the 0.75. And then we get a 2.25. Two 0.75, 3.25, and then a 3.75, and we're expecting something, we say about like 60 or 57, 55.78125. So that is really our estimate using the midpoint rule. Note our previous midpoint rule estimate was 54.375. We're still in the same ballpark. We generally suspect that with 6 rectangles we're getting a better estimate than with 3. It's not necessarily the case. There might be something funny going on. Likely that is the case in this particular scenario. This function isn't sort of that complex, really. 3 more. Same setup. We're going to do an lower sum, upper sum, and midpoint. But now we're going to use 15 rectangles. Okay, so this is starting to get a little bit annoying here. So this is, a little bit tedious here. So we're going to use a lower sum. Now, when I do that, my area, let's just go and look at the picture again. Here's our lower sums, and we go up to, there's 15. So we're going to get a picture like this. Starting to get a pretty good estimate. Still this sort of under the curve unshaded part, sort of that's an underestimate. We're missing those there. So this is going to be sort of small, but we're hopefully kind of zooming in on the answer here. What you would get when you do this, so this area, let's think about what we've got, is our interval from 1 to 4, that has length 3, and we're splitting into 15 pieces. So each one should be 3 over 15. That's 1 over 5, or 0.2. So our area, each rectangle should have width of 1/5. So we get 1/5. And then we're just going to add up, starting at f of 1, we're going to add the 1/5, which is 0.2. Next rectangle will be f of 1.2. You can look at the picture. Here's f of 1. We'll hide at 1. This should be at 0.1, 0.2. Next one's at 0.4. Next one we're going to do 1.6, 1.8, 2, and so on. So 1.2 plus f of 1.4 plus f of 1.6 plus blah, blah, blah. We're going to do 15 of these, and we're going to end up with f of, the last one is going to end up being 3.8. So we go up to 4 here, but we don't hit 4. So that last one sort of has a right endpoint of 4. Left, or the lower endpoint, is going to be 3.8 or 0.2 less than that. So this now is getting to be pretty tedious here. Point here is we want to sort of motivate, we want a quicker method. So this is doable. It just gets really annoying. In principle, you could do this and get as accurate a result as you want if you were willing to spend enough time. Let's calculate this one out here. So we get 1/5 times variables, whoops, missed that, variables, y variables, function y1 of 1 plus variables, y variables. So this is getting a little bit old. Let's maybe do this a little bit quicker. Let's go to stat, edit. I got some stuff in my lists already. I'm going to clear this out. Let's do 1, 1.2, 1.4, 1.6, 1.8. I'm going to put these here. 2, 2.2, 2.4, 2.6, 2.8, 3, 3.2, 3.4, 3.6, 3.8. So I put those there. I get 15 things in L1. Let's go to L2. And then what I'm going to do is just do variables, y variables function. I can do y1 of L1. So this will just rewrite this list. And the first one should be sort of f of 1, then f of 1.2, and so on. So what I get at the bottom here should be f of 3.8. So again, that's about 4. 4 would have given us, let's see, 4 cubed is 64, minus 4 is about 60. There's still some room to go up, but it's at least sort of in the ballpark here. So that gets us really our values. And now what I'm going to do down here, instead of typing that all out with the y1s, which gets a little bit old, I'm going to do 1/5 times. I'm going to put those in a list. I think it's, is it ops or it's math? Sum of L2. And now I should get a result that, let's see, before, let's think about what we're expecting here. Whoops. This one. So we did lower sums before. We had a result of 42.1875. We should get something bigger than 42.1875 here, because what we're doing when we look at these lower sums here is, again, the 42.1875, let's say I think we had 6 rectangles, now we have 15. In some sense, we should be getting sort of smaller errors here. Let's see what the calculator says. Spits out 50.4 here. So if I believe that, now I'm not sure if there's much rounding, but we're getting something like 50.4. So this apparently is 50.4. I'm not so concerned that you get that exactly correct. Probably you would use technology if you're really going to do this here. Okay. Next one. Whoops. We're going to use upper sum, which ends up being a right endpoint. So here our area, 1/5. Now, very much the same thing as doing the lower sums, except, let's go up to 15 here. This first rectangle is height 1, or no, sorry, height f of 1.2. Last one we actually get f of 4. So what we're going to get is essentially the same thing we had before, but we're going to start at f of 1.2, and then we're going to f of 1.4 plus blah, 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 and we're going to end up at f of 4 here. And what we should get is something bigger than our last answer, 50.4. Expect something bigger than 50.4 and something smaller than our last upper sum, 72.1875. So let's go check that. Now what I'm going to do to actually calculate this, I'm going to go to stat, edit, gives me my list. And I'm going to just change that 1. All that changed was the 1 changed to 4. So from the 1, so we've got this here. All that happened is this 1, we get rid of that, and we sort of add an f of 4, but I guess inside the parentheses there. So essentially that's what we have here. So I can go to my list, just change the 1 to a 4, and then I just make this variables, y variables function, y1 of 4. Could do the whole list again, but there's my 60 here. And now what I'm going to do is I can just really do the same thing I did before. So that gives me 62.4. So my answer here, well, let's do it in sort of this blue again, 62.4. Now we know our answer is really between 50.4 and 62.4. So instead of 15 rectangles, you could do 100 rectangles, 1,000 rectangles. This would get better and better and better. So these are Riemann sums here. And the idea here is that if you let the number of rectangles go to infinity, or actually the width of the widest rectangle go to 0, then these limits should approach each other here. So sort of these sums will get closer and closer and closer together, as close together as you'd like. One last idea here. We're going to use 15 rectangles in the midpoint rule. So this one, probably our best answer altogether. So, whoops. I'm having trouble getting to 15 exactly. I was almost there. There we go. There's 15. Again, this should be our midpoint. That should be pretty close. We have sort of an overestimate shaded here, and then an underestimate unshaded underneath the curve. So shaded above, unshaded below. Those two should just about cancel here. And to do that, whoops, we're going to get this area. It's going to be that 1/5. And what we're going to get, again, it's the 0.2, but the first one is going to be at 1.1. So we're going to move 0.2 each time. But this first rectangle goes from 1 to 1.2, so the midpoint is at 1.1. Hard to see there. But this one goes from 2.4 to 2.6, midpoint's 2.5. So what we're going to get is f of 1.1 plus f of 1.3 plus f of 1.5 plus some stuff. Last one should be at 3.9. It should be the midpoint of the last interval. Note it's 1 point, always the 10th digit is odd here. That works out. And to sort of do that somewhat efficiently, go to stat, edit. I'm going to clear out L1. Let's just do 1.1, 1.3, 1.5, 1.7. Probably could have added something to each of these, would have actually been more efficient. But can't do that anymore. 2.1, 2.3, 2.5, 2.7, 2.9, 3.1, 3.3, 3.5, 3.7, 3.9, and that's the last one. And then in L2, just go up to highlight L2, go variables, y variables function. I'm going to pick y1 of L1. It's going to just evaluate each of the elements in L1 at, using the function y1, spit out a bunch of values, and then I just do 1/5 of sum up everything in that list. Gives me 56.175. So really that's maybe our best estimate. You'll notice here, there's our last three estimates. It's pretty much in the middle of 50.4 and 62.4. Not quite, that'd be 56.4, but we're pretty close. Now, for the curious, what's the actual answer? Well, there's a number of ways to do this. Here, one is I can use my calculator. So if I go to Math, and toward the bottom on this first menu, there's an FNINT. So this is an integral. So what I'm going to do is do the x cubed minus x, or I could do y1 of x, comma, that's the function I'm going to integrate. I'm going to integrate with respect to x. We're going 1 to 4. Now what this is effectively going to do on this calculator is do the same thing we were doing, but instead of doing like 50 or 15 rectangles, it's going to do a whole bunch. So here's a picture up to 50, and you can see sort of that estimate's getting pretty big. Now probably the calculator can do up to like 1,000s, or I don't know, something where it can sort of, there's ways to get bounds on the error here. So it says the actual answer turns out to be 56.25. So at 56.175, we're pretty close. The other thing coming up is we're going to get an actual sort of quick, easy way to calculate this basically by hand. And so what that calculator just did is it approximated, this is a definite integral, from 1 to 4 of x cubed minus x dx. Now what will happen here is we're going to find something that's derivative is x cubed. So if you think about that for a while, that's x to the 4th over 4. If you differentiated x to the 4th, you'd get 4x cubed, and then the divide by 4 would cancel out that leading 4, you'd be left with x cubed. And then minus what would differentiate to an x, that's going to be x squared over 2. So you get used to this, and this will be second nature where these come from eventually in Calc 2. So if I differentiated x squared over 2, I get 2x divided by the 2. That would just give me the x. So I'm going to take these. A lot of times we'll write this. We're going to evaluate from 1 to 4. And what this means is we plug in 4. So 4 to the 4th over 4 minus 4 squared over 2. And then we subtract off when we plug in the 1. 1 to the 4th over 4 minus 1 squared over 2. See, 4 to the 4th over 4, that's 4 cubed, which is going to be 64. 4 squared is 16 over 2, that's minus 8. Minus, see, we get a 1/4. Let's just write it out that way. And then minus a negative, that'll be plus a half. So we get a 64 minus 8, that's a 56. 1/2 minus a 4th is plus 1/4. There's our 56.25, which actually matches what's going on here. Okay, so point of this worksheet here is to get you to understand how to estimate these really these areas on the curve using rectangles. It's a nice concept we'll use to approximate other things throughout the course. Here, in reality, we're not going to be doing a lot of this directly. It's more you want to understand sort of the underlying concepts here. So, and be able to do like this antiderivative or definite integral. We'll get terms like that later on. And I think we are then done with this worksheet.